is my cat, Elizabeth, though lately she's been more of a guinea pig than a cat. She caught a nasty new feline virus, and my vet gave her an experimental drug to treat it. 2 other drugs are also being tested. The drugs are randomly assigned to sick cats to determine if there is any significant difference in effectiveness. To analyze the results of my vet's study, we could classify the outcomes as got better and stayed the same. Now, if there were only 2 drugs, we could use the inference test for proportions from the last program. But here there are 3 populations, 3 different treatment categories, and for each, the outcomes could be got better or stayed the same. So we need a more flexible way to handle categorical variables, and that's what we'll explore today. We'll see that two-way tables let us compare the distribution of a categorical variable, like drug test results, in several populations. We'll learn that two-way tables can also be used to measure relationships between 2 or more categorical variables in a single population. And we'll meet the chi-square test, which tells us the significance of the relation in a two-way table. To begin, let's make a two-way table for the results from my vet's study. We put the 3 types of drugs in the rows and the possible responses to the drugs in 2 columns. Remember that with two-way tables like these, our data must be categorical, a yes-no response to a question, or data that are lumped together into broad classes. Here, the 3 treatment groups represent 3 different populations, and the response of the cats is measured with a yes-no type of categorical variable, whether they got better or not. Since this table has 3 rows and 2 columns, it's called a 3-by-2 table. A table size is always given as the number of rows by the number of columns. If we had 4 rows and 2 columns, we'd have a 4-by-2 table, and so on. In this program, we're going to learn ways to analyze these kinds of tables using the chi-square test. Our main goal will be to decide if the data show a statistically significant relationship, or if nothing but random variation is at work. In other words, we'll be performing a significance test. Let's see how such tables are used by taking a look at some research you can really sink your teeth into.
If we are what we eat, then our teeth should say something about us. And that's what Dr. Fred Grein is looking into. Dr. Grein is no dentist. He's an anthropologist who studies fossil teeth like this one to piece together the story of human evolution, a tale with many chapters still missing.
The fossil record itself is incomplete. We have a dearth of evidence, as it were, to fill in many of the gaps in our knowledge. And that it's therefore important that every scrap of evidence be analyzed to its fullest.
What's being analyzed here is the tooth surface of a species of early man, Australopithecus robustus. Etched into each tooth lies the answer, Grein believes, to a controversy over how closely humans are related to robustus. The players in this 2-million-year-old family feud are robustus, a species called Australopithecus africanus, and members of our own branch, such as Homo erectus. For years, anthropologists believed that Africanus was the last common ancestor of the robust line, which became extinct, and the line which led to modern humans. Was robustus a close relative of ours, whose massive teeth and skull evolved by eating a greater volume of the same food as Africanus? If so, why did robustus look so different from its presumed ancestor? Could he have been another species altogether, whose large teeth and body were the result of a completely different diet from Africanus?
We've got an Australopithecus specimen in there. Let's center the...
To answer these questions, Dr. Grein compared teeth from robustus and Africanus fossils to see if they differed from each other. First, a scanning electron microscope magnified the tooth surface. A lifetime of chewing leaves distinct wear patterns, which can be broken into 2 categories, pits and scratches.
Okay, I'd like to see what the proportion of the total of this micrograph here is made up by these deep scratches that are coming up in red. So why don't we see if we can get a histogram of that?
Okay.
For each magnified surface, the number of pits and scratches was tallied.
Okay, how many scratches have you got within 10, 20 degrees of buccal lingual there, something?
Using a 2-by-2 table with counts of pits and scratches for both robustus and Africanus, a chi-square analysis compared the distribution of wear patterns. The robustus teeth have a higher incidence of pitting, while Africanus has a greater number of scratches. Next, to find out what differences in diet produce these patterns, a new set of analyses was run, this time comparing the samples to primates whose exact diets are known.
The chi-squared analyses showed that the robustus patterns didn't differ significantly from the patterns shown by monkeys that eat palm nuts and are known for being able to crack these very hard nuts. Australopithecus pattern, on the other hand, was found to not differ significantly from monkeys that would eat softer objects.
The pitting on robustus teeth indicated they ate hard objects, such as bark or nuts, while the predominance of scratches on africanus teeth meant their diet consisted of soft foods, such as fruit and leaves. With this finding, the human tree needed rearranging.
Robust Australopithecines were not just large variants of A. africanus, and therefore they were not just simply a phylogenetic offshoot that increased in size from A. africanus, but rather that there were fundamental differences between them. And it would fit quite handily with the evidence on phylogeny as suggested by the black skull that was recently found, that in fact the robust Australopithecines have a very ancient history, quite separate from the lineage that would have led to humans.
So members of our branch, such as Homo erectus, can no longer call robustus a close cousin. With this new knowledge, scientists redrew our family ancestry to change the place of robustus. Working with just a few scraps of evidence, these insights into diet have advanced our understanding of the roots of the human family.
A two-way table of data from the fossil teeth study lets us compare a single categorical variable, type of tooth wear, between two different populations, africanus and robustus. Since this makes a 2x2 table, we could use a z-test for two proportions, but instead we'll use this example to learn our new chi-square method. We'll label the columns scratches and pits. The two rows are the two species, africanus and robustus. Then we can enter the counts of pits and scratches. To see how the species differ, let's convert the counts to percents for each species. In this case, the proportions show that robustus had roughly equal numbers of pits and scratches, while africanus had distinctly more scratches and fewer pits in its teeth. Looking at the percentages gives us a good overall feel for the data, but for the inference procedures we're about to learn, we need to work with the frequency counts. Now the question becomes whether the differences in wear patterns are significant. After all, we wouldn't expect the patterns for the two samples to be identical. The observed differences might simply be due to chance, so what we need here is a significance test to tell us the probability of getting our result from random variation alone. Our null hypothesis is that the tooth wear patterns of the two species are the same, implying that there were no differences in the diets. The alternative hypothesis says the patterns are different, and therefore the diets were not the same. The first step in doing inference for this two-way table is to figure out what our results would look like if the distribution of pits and scratches were the same in both populations. We do this by calculating the expected counts for each entry in the table. First, we write the sums of the values in each row at the right of the table. Then the entries in each column are added. Finally, the totals themselves are added and put in the bottom right corner. Notice that the sum of the row totals equals the sum of the column totals. Both are 728, the total number of observations made. Now we need to find the expected count, which is the result we'd expect if the null hypothesis were true. For each cell in the table, we multiply its row total by its column total and then divide by the table total. For example, the expected number of scratches in the teeth of africanus is 290 times 415 over 728, which is about 165. The expected count of pits in the teeth of the same species is 290 times 313 over 728, which is about 125. Doing the math for the other two cells gives us a picture of what we would expect if there were no differences in the distribution of tooth wear between the two species. The expected counts themselves are not equal because there were fewer total pits and scratches in the teeth of africanus. Notice that the row and column totals are the same for the expected counts as for the observed counts in the original table. This should always be true, and it's a good way to check your math. Now, if the observed counts are far from the expected counts, we'll suspect that something other than chance is at work and will declare the null hypothesis false. To do this comparison, we use the chi-square statistic, written like this, invented in 1900 by the statistician Carl Pearson. The chi-square statistic is refreshingly simple. For each cell, you subtract the expected count from the observed count, square the difference, and then divide by the expected count. Do this for all the cells in the table and add the results. The chi-square statistic measures how far the observed counts deviate from the expected counts. The smaller the number, the closer the fit of the data. A chi-square of 0 means the data exactly fit the predicted values. In the fossil teeth data, the observed count in the first cell was 200 and the expected count was 165.3. So we subtract the two, square the result, and divide by the expected count, giving us 7.3. Doing this for each cell and adding the results produces a chi-square value of 28.2. Remember that small values for the chi-square statistic mean there's a good fit between the real data and the model. From our experience with other test statistics, we can guess that 28.2 is a large value, meaning the real data vary quite a bit from our model. In other words, we've produced evidence that the null hypothesis is wrong. There appears to be a real difference in tooth wear patterns and diets between the two species. In this case, a chi-square as large as 28.2 would occur by chance less than 1 time in 1,000. We'll see where that p-value came from in a bit. First, let's see how the chi-square test is being used in some medical detective work.
I came home from work one evening and I was getting undressed, and I don't know how, but my hand slipped across my breast and I felt this huge lump, and I had never felt it before. And my son heard me because I started to cry because it was such a, a traumatizing sort of thing.
That traumatic day 3 years ago was the start of Teresa Murphy's fight against breast cancer. Her disease was aggressively treated with a mastectomy and chemotherapy, and today she is well. But for many older women, the same is not true. There is now evidence that older women are less likely to receive the appropriate treatment for their disease than are younger women.
I'll just come in a little bit more. That's good.
Researchers at Brown University conducted a study of how women in different age categories were treated.
Okay, now this is the medical record abstract form.
Yes.
We ended up with 494 women with breast cancer identified in the hospitals in Rhode Island. We broke those women into 3 age groups, ages 45 to 64, 65 to 74, and 75 to 90.
Only women healthy enough to receive the full treatment were included in the study's chi-square analysis. For women in all the age groups, the accepted treatment for breast cancer that has spread is a mastectomy, surgery to remove the breast, and follow-up chemotherapy. Of women in the 75 to 90 age group, only 1/3 received chemotherapy after surgery, compared to 2/3 of the younger women. This difference was statistically significant at the .003 level, a disturbing trend.
Older women are not being given the same alternatives in terms of treatment. I think that the bias in the term on the part of the physician is that A, he or she is not sure the patient can tolerate the therapy. And I think that's an age bias. And B, I think whether it's conscious or subconscious, there's this idea, well, she's already 75, So I'm not going to treat her like a 45-year-old woman where I'm really shooting for a cure because she doesn't have that long to live.
In fact, women 75 years old will live on average 12 years. Without chemotherapy, cancer is likely to recur within 5 years. So a physician's age bias may be affecting the quality and the length of life for the elderly woman. How to draw up discrete age categories from the continuous group of all women's ages is a difficult choice. The researchers decided on 3 age groups. But how would narrowing the categories affect the results?
While we find with 3-category age variable, we end up with a p-value, a probability value from the chi-square distribution that is something on the order of .003. By the time we're up to a 5 or 6 or 7 category age variable, we're at a probability value of just 0.03.
How about where the actual scar was? Does that?
While even a p-value of 0.03 is often viewed as significant, it reveals the impact that choice of categories can have. The conclusion drawn here is that health professionals are discriminating by age, a bias physicians need to be educated about.
They may not be aware even that they're really not doing the whole 9 yards on the older patient. So their bias bothers me, but I think that's a correctable item now that it's been identified.
The importance of doing the whole 9 yards is clear from success stories such as Teresa Murphy's. Getting the definitive treatment enabled Teresa to go on with her life, giving to her the chance to make her older years as full of life as any other years.
Oh, well, that's no good.
I just want to work for 3 more years, and then I'd like to be able to retire and just go and visit my friends and just have a good time. Just enjoy the rest of my life.
Another comparison in the breast cancer study was between age and the appropriateness of diagnostic tests. In other words, whether women were given a mammogram and breast lump biopsy. Both these classifications, age and diagnostic tests, are categorical. We want to know if there's an association between them. This is a relationship within a single population, which is different from comparing two populations as we did with teeth. Fortunately, we can use a two-way table and the chi-square statistic in both cases. We'll use data from the breast cancer study to see how to calculate a p-value for chi-square. Here's a 3x2 table for the number of women in each age category who did or did not receive the appropriate test. As before, we'll express the counts as percentages of the row totals to get a preliminary comparison. In this case, we can see that older women were indeed less likely to receive the appropriate test than younger women. Now we use the counts to compute a chi-square statistic to determine if the relationship is statistically significant. Here are the row, column, and table totals. As before, we calculate the expected value for each cell by multiplying the row total by the column total and dividing by the table total. With the values for observed and expected counts in hand, we find a value of 7.35 for our chi-square statistic. Now we need to convert that number into a p-value. We do that by comparing the value of the test statistic with critical values for its distribution. We did exactly the same type of thing in finding p-values for our z and t statistics. Here's the distribution of the chi-square statistic when the null hypothesis is true. Obviously, the chi-square statistic marches to a different drummer than the z and t statistics. It's not at all symmetric. It's plainly skewed to the right. This distribution shows us the behavior of the chi-square statistic in a very large number of samples. If you think of the curve as a probability distribution, it begins to make more sense. The curve starts at 0. As we saw, a chi-square of 0 means there's a perfect fit between the real data and the model predicted by the null hypothesis. You can see from the curve that the probability of getting chi-square values near 0 is high, and then drops off steadily as the values increase. Also, just like the t-distributions, chi-square is really a family of distributions, one for each degree of freedom. As degrees of freedom increase, the distribution becomes less skewed. Finding the degrees of freedom for the chi-square statistic is easy. If our two-way table has r rows and c columns, the degrees of freedom for the statistic are r-1 times c-1. So for a 3x2 table like we have in the breast cancer diagnosis study, the proper degrees of freedom are 3-1 times 2-1, which equals 2. To see how significant a particular chi-square statistic is, simply compare its value to a table of critical values with correct degrees of freedom. So we look in the row for 2 degrees of freedom and find that 7.35 is very close to the value for 0.025. The p-value is very close to 2.5%. This p-value is small enough to confirm that there is indeed a significant difference in the use of appropriate diagnostic tests for breast cancer among different age groups. When using the chi-square test, remember that with large samples, even a very small association will appear statistically significant. The general rule is use a comparison of percentages to get a sense for the size and strength of an association. Use chi-square calculated from counts to find out whether an association that large is likely to occur by chance alone. As we've seen, one of the challenges of using chi-square is arranging your data in the form of discrete populations or categorical variables. This issue is at the root of a long-standing debate surrounding one of the grand old men of science.
Gregor Mendel, the 19th century monk and plant breeder, is known as the father of genetics. In a pea garden at his abbey, Mendel first quantified the laws of heredity. For example, he crossed yellow and green peas to produce offspring in distinct ratios of 3 yellow peas to 1 green pea. But Mendel's reputation has been clouded by accusations of cheating. Statistician R.A. Fisher ran a chi-square analysis of Mendel's pea studies and concluded they were simply too good to be true. The chance that Mendel's results would agree as well as they did with theory is only 1 in 30,000. Did Mendel cheat?
What's the assumption behind a statistical analysis of a biological system? Well, the first is that there are such things as ideal categories.
Science historian Robert Root Bernstein believes that this controversy is due to a basic tension between statistical ideals and the way nature works. Mendel came across some pea plants that just did not fit into his theoretical categories.
He's recognizing explicitly that there are difficult to classify seeds or plants or flowers or whatever. He thinks he has to do something about them. I mean, he's going to have to divide them into one category or another somehow. If he does that, doesn't that amount to fraud? Well, I don't think so. Okay, when you look at them, you'll see they're essentially the same number of purple as yellow. So
to prove his point, Professor Root Bernstein and his students reproduced the problem Mendel had with indeterminacy, which is how to place hard-to-classify peas into discrete categories.
Do you want us each to have our own?
Yes, there won't be enough for everybody, so you'll just have to share.
I gotta add another thing.
One half of the students classify the kernels according to theory, having to fit all kernels into just 2 categories. The other half of the class examine the same ears of corn, but in addition to the 2 categories, they have a third choice, difficult to classify. The students find out the task is not a simple process.
Well, this one's definitely red.
Yeah,
but like this one here, and this one looks pink to me too.
And the one right before that, it's kind of hard to tell.
I don't know, I counted that one as red.
Did you? I was thinking about that.
I don't know, I suppose I should take it off.
9, 10, 11, 12. I still think that was yellow.
Because it's closer to this color here than it would be to the yellow.
But that's what...
Each group then totals up their counts. A chi-square analysis is run on the group that only had 2 choices. Their results are fairly close to the 50-50 ratio predicted by genetic theory.
Theory is correct. Okay, so we are more or less in the right ballpark. This is what we expect our good data to look like.
The other group gets 5% indeterminate kernels. They apportion these where they need them to exactly match the theory. Then they perform a chi-square on how significant these results are.
Is 0. There is no probability that we could get this just by accident. So what we have here is data that is way too good to be true. All because we simply left the determination of where we wanted to put the indeterminates for the end when we already had preliminary results.
Mendel had fewer indeterminates than the students, perhaps just 0.5%. But how he categorized them makes the difference between good results and results that look too good.
I think what he was simply trying to do was test his theory. The theory said that the results would come out looking more or less like a 3-to-1 ratio, and he knew that he had some problems with a certain number of individuals. What am I going to do with them? He sits down and he does the best he can. No matter what Mendel did with his data, he's not a cheat and he's not a fraud. Essentially, anyone who is working with this data comes up against the same problem. Everybody sees certain ones that are difficult to classify, and you have to do something with them. So everybody is going to recognize at some point, whether explicitly or not, that there is this tension between the statistical ideal and the biological reality. And in trying to stuff the biological reality into the statistical ideal, you're going to run into the small number of problems.
That one? That's purple.
This is purple.
That's purple.
No,
totally.
that's light, very light purple.
It's purple. Let's start again. Calling purple, right? Purple.
The moral of the Mendel controversy is that you need to be careful in constructing categories for your data. But once they are constructed, valuable information can be extracted by arranging the data in a two-way table and performing a chi-square test. In the next program, well, I guess you'll have to wait and see for yourself what the next show's about. I've got a hungry guinea pig to feed.
This edition of Against All Odds can be seen again on Saturday week at 10:30.